everyone. Welcome to the latest in Pharmaron's DMPK Insights series of podcasts. My name is Claire Henson. I lead the imaging group here at our UK-based Integrated Metabolism Department, and I'm delighted to be joined today by Professor Josephine Bunch. Josephine completed a Ph.D. in Mass Spectrometry imaging at Sheffield Hallam University, followed by a postdoc appointment at the University of Sheffield. Josephine then led a research group at the University of Birmingham, where she also lectured in chemistry and imaging. Josephine is currently based at the National Physical Laboratory, where she's co-director of the National Centre of Excellence in Mass Spectrometry Imaging, or NiCE-MSI, and is also chair of Biomolecular Mass Spectrometry at Imperial College London. As if that wasn't enough, she is also currently leading the Cancer Research UK Grand Challenge programme, which is a really exciting project that I hope we'll hear a little bit more about. So welcome, Josephine.
Good morning.
So Josephine is with me today to discuss the current state of mass spec imaging and to talk about where we are likely to see exciting new developments and how they might impact DMPK and drug development. But before we get into that, I would really love to hear a little bit about the Grand Challenge programme that you're involved with and what you hope to achieve with all that.
The Cancer Research UK Grand Challenge programme is drawing to an end at the moment. So this is a programme that started in 2017 that we put together as a large collaborative proposal in 2016. And we responded to Cancer Research UK's inaugural call of the Grand Challenges. They posed 7 questions, I believe 7 questions at the time, to the international community, all of which represented some of the big roadblocks preventing our ability to affect improvements in diagnosis and understanding and developing appropriate treatment regimes for cancer patients. So the programme that we put together responded to the specific challenge of find a way of mapping tumours at a molecular and cellular level. And we're one of 2 programmes that have been running since 2017 that have addressed that question. There's also a team in Cambridge called the IMAX programme. So our project put mass spectrometry imaging at the very centre of our proposal. And when we conceived of this, we started off trying to build a new measurement framework. We took a very agnostic approach of the problem. We didn't decide which molecules we felt were going to be the most informative. We didn't pick particular cell types that we wanted to focus on. Instead, we put together a program where we wanted to address an understanding of spatially resolved metabolism across diseases in colon cancer, glioblastoma brain cancer, breast cancer, and pancreatic cancer. And we, as a consortium, recognized that to do this, we needed to develop imaging routines that could be used to image large numbers of patient samples, as well as single sections or multiple sections from preclinical research models, as well as spheroids, organoids, etc. So this gave us a multi-scale problem as well as a large analytical footprint. And so we brought together the innovators and leading practitioners of a whole range of different mass spectrometry imaging approaches. And we developed a pipeline that starts with in vivo measurements using techniques such as the iKnife, which is a mass spectrometry surgical approach, but also non-invasive techniques like hyperpolarized MRI and a range of different methods for rapid imaging of whole slides. And then high resolution methods where we're looking at single cells and within single cells. And we have worked as a group over 7 years now to refine that approach and to learn consistently about the relative merits of the different modalities, when to use them, how to improve them. We have done an awful lot of rigorous, often seemingly unglamorous comparison and metrology to really understand where our blind spots are, because of course it's only as informative as your awareness of what it can and can't do. And in the last couple of years of the project, we've really been using it in earnest at ever increasingly large sample sets. So, for example, the largest sample set that we have explored is a set prepared in tissue microarrays of 3,000 patient cores. And the work is never finished, as you can imagine, although the program will finish this year. But I think we leave the challenge in a very different state and the field in a very different state to when we started.
Yeah, it sounds amazing. And I had a look on the project's website. It sounds like you've really gathered together a sort of dream team of who's who in imaging and mass spec imaging. It looks fantastic. How many people have been on the project working together?
We've had a lot of people, an enormous number of people. I mean, we bring together 8 sites. I think now that we're in our 7th year, we are able to attribute the fantastic results now to the efforts of over 70 people. Of course, they haven't all worked on that program full time, particularly at NPL, the National Physical Laboratory. We've been able to draw on the skills of a lot of our staff, but they haven't been involved necessarily full time. And we've obviously had staff leave the program as they move on to different career challenges. But yes, we have gained the benefit of 70 people's wisdom so far on the project.
Yeah, it's amazing. And just a final question for this point. Just they say necessity is the mother of invention. You must have had to sort of adapt and perhaps develop new techniques. Have you for really focusing on what you wanted to focus? Have you really come up with something that you're particularly proud of with this?
I think there are many things that the consortium are very proud of. I think something in particular I'd like to highlight from the period of the Grand Challenge funding is the techniques that we have developed to allow us and others in the field to image samples that have been prepared by formalin fixation, paraffin embedding. Although it has been possible to use mass spectrometry imaging for these methods in the past, they have typically required quite extensive sample pre-treatment and other antigen retrieval type protocols to be applied before you could use mass spectrometry imaging. And then the information from those mass spectrometry imaging methods was often somewhat limited. And we have developed approaches and protocols within the consortium, all of which actually use infrared lasers to sample the material, but have very different ionization mechanism features. And we have found these very powerful methods for formalin fixed samples. And I think that will be so important because although we've been able to gather some fantastic results from all of our work in fresh samples, the pathology workflow preference, histopathology workflows, typically in the NHS, for example, still rely on rapid formalin fixation of the majority of samples for other microscopy workflows. And so being able to access samples that may already have been collected, so thinking of biobank samples, archive samples, using these techniques as well, will be increasingly important, I think, as these techniques are taken up more widely.
Yeah, absolutely. No, that's great. Okay, well, thank you. It sounds absolutely fascinating, but it's such a huge task when you consider the thousands of endogenous species that you're coming across, and just I don't know, the computing power alone must be quite phenomenal for all of this.
I mean, I think this is a field that has continued to mature over the last 10 or 20 years since its original introduction at the end of the 90s, most famously. And the way in which we're able to use it now is at least 50% due to our ability to make sense of the information. as the techniques have matured and become more reliable and the sensitivities improved, our knowledge of how to handle the increasingly large and hyperspectral data has been critical. I'd say in even the Grand Challenge program, more than half our effort has been computational or concerned improvements in data analytics.
Yeah. Okay, so of course, my background is in radiolabeled imaging using quantitative whole body autoradiography, which gives brilliant spatial information about the distribution of total radioactivity in tissue sections, but obviously no information about what that radioactivity is comprised of, metabolites or parent. So the advent of mass spec imaging for us was met with huge excitement and across DMPK disciplines. Although there were limitations initially, of course, but there have been huge advances, as you've been saying, with sample preparation, instrumentation, data manipulation over the last decade or so. So what do you consider to have been sort of the most exciting or significant breakthroughs for MSI in recent years?
There are many. Some that I would like to highlight. The introduction of desorption electrospray ionization, although very tricky to use for new users when it was first introduced, and perhaps in the early days less reliable than the other modalities available, we have quickly learnt that sampling with solvents allows us to extract all the more classes of analyte without the requirement to carefully select, for example, a matrix compound that might be used in MALDI. And once you're able to show people the breadth of molecular coverage that can be achieved, then people's awareness of what they could do with that really grows. And so if we think about how this might be used within pharmaceutical companies, I think going back 10 years ago or more, there were a number of pharmaceutical companies very interested and already adopting this for, as you've already described, powerful experiments where they're able to image not just a parent drug, but the metabolites as well, and increase the specificity of information that they were already able to gather with autoradiography. And I think combining those workflows and allowing the additional quantitative information that does come from the QWBA was a very nice solution to a number of PK problems. But of course, the mass spectrometers were measuring an awful lot more all the time. And as we've been able to annotate more of that information, is make sense of all the peaks that were already there and increase the number of peaks that are detected, we've come to realize that this is a technique that can be used for PK/PD studies simultaneously. And so it's not just an understanding of the fate of the drug itself and its distribution and metabolism, but an understanding of how that alters the environment around it and vice versa. And so now we're able to consider how the techniques could be used to understand other features of that whole experiment, all the way through to even starting to identify not just areas of drug resistance, but perhaps even the mechanisms driving that drug resistance in a single experiment.
So there's a real buzz now also about how far we can push the limits of mass spec imaging. So not just in terms of pixel size and mass resolution, but also in terms of application to specific disease states and personalized medicine. So can you talk about any highlights or interesting sort of technologies that you're using to really good effect now in that regard?
I mean, we're still in many of our more discovery type experiments pursuing quite a complex workflow that incorporates more than one modality. And we do this for a number of reasons. One is to gather information across multiple scales, but to do that not just to produce beautiful data sets, but to actually try in those projects to deliver the mechanistic understanding that's really required. Because I think for a while, when we think about our our hopes of using this for patient stratification or selection even of patients for appropriate trials, we've been able to differentiate features of disease for a while, but whether or not we've been able to identify potent or actionable biomarkers that allow us to rapidly make those selections and understand why, I think we're only just starting to see examples from our lab and elsewhere around the world where that is now becoming true. And it will still be a long journey, as we all know, in emerging modalities, which, although increasingly mature, this will remain, and an awareness that it won't be solved by a single approach. And so, as we find ourselves almost at the forefront of a new field of spatial biology, and this is what we see so much excitement of. Spatial biology remains a field under construction where many exciting things have happened in the last 5 years, not least the complete revolution in what we can do with spatial transcriptomics. And so we're now newly in a position that mass spectrometry imaging has reached a maturity of performance that people are starting to take real notice and become increasingly innovative in how they can use that. But we're also able to pair it with other experiments, for example, spatial transcriptomics, to really understand in a multi-omics format what's actually happening, and how we can understand, for example, differing phenotypes in heterogeneous disease problems.
Yeah. So we talked a lot about, people talk a lot about label-free imaging with mass spec imaging, and of course that's a huge benefit over the sort of imaging that I do. But I've noticed that there is sort of some labeling creeping back a little bit into mass spec imaging. We've got the imaging mass cytometry, which tags for sort of proteins mainly, I guess, and sort of MALDI IHC as well. So, I mean, obviously, we're sort of coming to realise that a sort of integrated approach is really useful for this type of imaging, and that we are going to have to draw on other things rather than just the label-free type of mass spec imaging. Have you used those sort of more label?
Yeah, we use them all, and the way I think to look at it, that in many of the experiments we want to be able to perform targeted experiments and gather untargeted information that we can then explore in an unsupervised manner. And there is no need to replace impressive techniques, and as you've already mentioned, mass cytometry is a great example of that, which is really just exploiting what we've used for decades in immunohistochemistry, but improving the number of molecules that we could look at in experiments, so that we're no longer limited by interference from overlapping colors. In a fluorometric experiment, we can use a metal tag and take advantage of a mass spectrometer, and those are by far more powerful ways of examining proteins in cells and tissues than the current methods for untargeted mass spectrometry imaging of proteins. However, as a discovery tool, you will only gain information on what you set out to examine. You have pre-decided the molecules that you are looking for. And so I think recognition of what information you're going to get or not get is so important. I think there are other areas that we're also really taking advantage of, not labels in quite that manner, but incorporating labeled standards into even our untargeted experiments. And we could do this for two reasons. I mean, the use of isotopically labeled standards in mass spectrometry imaging methods, either to aid quantitation, but also to allow us to perform flux experiments and tracing experiments to understand the fate of a metabolite through complicated pathways, is so important.
So you mentioned quantification there, quantitation. How close are we to having sort of reliable quantitation? I know with things like MALDI, MSI, I think quantitation is being used currently. How reliable is that, and where can that go, do you think?
I mean, I think it's a real problem. I mean, I'm always unpopular when I say this. It is not a quantitative technique. And even though we have some strategies to improve that through, again, the use of standards, for example, they're not easy to universally apply, because the reason these techniques are not quantitative is because of variable ion suppression. And since there's always a complete lack of ground truth or knowledge of what that actual sample location or matrix contains, it's very difficult to adjust that completely. But in instances where you are only hoping to provide a quantitative estimate for a single compound, and you have an isotopically labeled sample, and you have a well-validated calibration routine, you can certainly improve it. In terms of gaining a quantitative estimate for something from an unlabeled or untargeted data set, I think there's a very, very long way to go.
So, okay, if we can look at the future for a moment. So where do you see, I know we've covered this a little bit already, but where do you see the most exciting areas of growth taking place now? And how can we make the best use of those innovations in sort of the drug development space?
I mean, as we've mentioned, I think the techniques performance are now ready to be far more widely used in PK/PD studies than they currently are. And as mentioned, not just looking for the drug itself, understanding areas or problems earlier in drug development processes in the preclinical testing around drug resistance, being able to do that mechanistically and in a spatially resolved manner. But I think the real future will be the ongoing quest for development of personalized medicine approaches and our ability to stratify patients. And that will require us to examine large numbers of samples that we have already collected from both preclinical and clinical trials, which is why being able to examine previously collected samples will be so important. And thinking about consistently pushing the reliability of these approaches, because people often don't want to hear it, but these techniques still show a variability, particularly in non-expert hands, that is not commensurate with being deployed alongside much more mature techniques. So, for example, the other techniques that you might use in these workflows, you would at least understand your uncertainty estimate. But actually, we don't have a propagation or an uncertainty budget for mass spectrometry imaging yet, for either individual modalities or when they're applied in concert in complicated workflows. And so, here at the National Physical Laboratory, we very much see that as our job to support people in the background. We are the UK National Measurement Institute, and metrology is our main focus. But I think without those things in place, then it will be quite difficult to see this widely in the future. The question in 2045, will this be used alongside standard practice within the NHS in histopathology? I don't know, but there's a lot of improvements to make until then. Will it have been part of the portfolios of evidence that have identified the biomarkers that can be screened very rapidly using other imaging techniques? Yes, I think it will. I think they will be.
Yeah. So, I mean, I've seen quite a few techniques coming through in papers and things where they're really combining a lot of different techniques. So, sort of MALDI with ESI and laser microdissection, and then coupling that to LC-MS. So are we seeing a lot more of that kind of different combinations of techniques to really get as much information as we can?
Yeah, we are. I mean, a nice approach is to use a rapid mass spectrometry imaging method, computational and machine learning based segmentation exercises to understand regions of interest, to use those segmented maps to direct collection of a sample that might be using something like laser capture microdissection, to then take advantage of more traditional techniques such as LC-MS for a quantitative estimate of metabolites in that region, is a laborious but powerful workflow. I think some of the MSI coupled to laser capture microdissection protocols that many of us were developing 5 years ago have somewhat been superseded in need by the advent of things like spatial transcriptomics. I mean, many of us were doing that to excise material to then go through single cell or RNA-seq type protocols. But with GeoMX and CosMX platforms, perhaps we don't have to undertake all of that. I mean, I think we are all now newly learning again which are the critical parts of these, often quite expensive experiments to perform. So there will probably be another number of years where we have to perform all of these experiments before then, with hindsight, we realize the simpler way of doing it.
Yeah. So you mentioned expense there, and obviously a lot of these instruments are very expensive. Do you see the cost of those coming down? I mean, I guess eventually they will, perhaps, but are things going to become more mainstream? Are we going to see smaller, more compact instrumentation for high throughput sort of screening? Or
it's a good question, and a very difficult one to answer without a crystal ball. But interestingly, if you look at available information and compare it to other fields, and again, transcriptomics is an excellent field to compare it to, unlike that field, no, the cost of mass spectrometry or mass spectrometry imaging has not come down. In fact, quite the opposite. But also the performance of those instruments has gone up. And so we are still in a phase where they cost more and you get more for them. They're also being more widely adopted, and so there is a volume argument that may or may not catch up or tip that over. I think that in the future, if I had to guess, there will be relatively few labs performing very complex mass spectrometry imaging experiments with very, very high-end instrumentation. And there will be many more labs able to use what they have developed in simpler instrumentation for screening purposes, not dissimilar to what we've seen with other mass spectrometry areas where discovery is different to validation, for example, where you can move things over to a triple quad screening assay that you might have had to use very different instruments to have decided what to look for in the first place. But anything is possible. Who knows? And it is clear that the ease of use and the cost and the footprint of the instrumentation will limit some widespread uptake.
Yeah, I mean, you're right. Who knows exactly? I mean, we've come a pretty long way, really, in the last 20 years or so. So, yeah, who knows what the next 20 years or so holds. Just picking up on something you said right at the beginning, actually, the iKnife. That sounds fascinating. Do you think you just explain a little bit more about that and how it's used?
Certainly. So the iKnife is the absolutely brilliant invention of one of my colleagues, Sultan Takats. He's at Imperial College London, and very proud to have been able to work with him for a number of years. And he's also part of the Rosetta Consortium. And he was able to see something that, when you hear about it, is almost so elegant that you can hardly believe that somebody hadn't managed it before. But in standard surgery, using a long introduced diathermy type device, it cauterizes tissue almost as it cuts it. You would describe it as a surgical smoke. I mean, to a degree, there is a burn and an incision. And to Zoltan, one of the most innovative mass spectrometrists of our time, he invented desorption electrospray ionization as well. But to him, this wasn't a surgical smoke. This was a rich, gaseous, desorbed plume of molecules and ions that could be harnessed for real-time tissue identification. And so over the last, I would hate to butcher the true dates, but I believe for quite a while now, starting with fairly primitive devices, they have worked out how to sample that gaseous plume, and in doing so have developed a new range of different techniques, which are all based on something called rapid evaporative ionization mass spectrometry, which aids the assistance and ionization of that plume. And more recent generations of The original iKnife now incorporate infrared lasers. We use these both for in vivo and ex vivo applications. Further innovations based on things like self-guiding fibers so that you can perform imaging alongside techniques such as endoscopy. And I genuinely believe this will be a revolution in the future of healthcare.
Yeah, that sounds fascinating, really. We could probably talk about this all day. But no, I think that probably just about brings us to the end of this discussion. Thank you ever so much, Josephine. It's been really, really interesting. Yeah, thanks for being here today. So thank you all for listening to this episode of Pharmaron's DMPK Insights series. We'd like to remind you that our DMPK webinar series is also available on demand, covering a variety of key questions related to DMPK science in drug discovery and drug development. So do stay tuned for more podcasts in our Pharmaron DMPK Insights series. So thank you and bye for now.